video, we're going to discuss data displays. So what is a data display? Data display is a graphical representation of anything that's summarizing the data. And most importantly, it should be something that's easy to read. It should be palatable for the person who's interpreting the data. So what it's not is just a big table of data, right? If you have a spreadsheet and it has lots of information on it, there's certainly ways that you can grab that data and show it in different pictures to kind of convey certain ideas to people. Depending on the kind of data that you're using, you may want to use one of the following types of displays of data. So we have 5 of them that we're going to look at today: the bar chart, the histogram, the pie chart, the line graph, and the scatter plot. We'll see some similarities in these first two. The first two we look at are bar graphs and histograms. And what we see is the bar graphs are used to represent frequencies categories of data. So bar graphs usually have on the bottom axis here, we have certain data that we put categorically. In this bar graph that we're looking at in this example right here, it looks like we were looking at letter grades. And so what we did is we took all these scores on a final exam and broke them up into F's, D's, C's, B's, and A's, and then counted out how many of those there were and put that information here. So we can see that in this bar graph, a couple things that are different between this bar graph and this histogram. Well, first, they're using the same data. So that's really important. Even though the pictures look very, very different, the data is the same. In the bar graph here, some important things to notice is that we have this gap in between the bars. And the reason why, for bar graphs, things are categorized where you either fit into a particular group or you don't. And so it's not a continuous set of data. Whereas in a histogram, if we look at the numbers down here, this particular example in the histogram, what we did was we took all these numbers and broke them up into increments of 10, 10, 20, 30, 40, 50, 60, and so on. And then took all of this data and categorized it basically by how much you are. Are you less than 10? Are you between 10 and 20? Are you between 20 and 30? And so on and so forth. And so what it does is it shows us 2 separate ways of looking at the same material. One, for the histogram, the bars are touching and the data is continuous, whereas in this one, we have gaps between the bars and the data is not continuous. Both of them use frequency along the vertical axis. So frequency is just telling us how many times you occurred. So over here, I can look at how many A's, B's, C's there were by looking at the height of the bar graph. It takes some investigation if we want to know exact values, but on a quick glance, what it shows us is kind of a distribution, right? I can see there wasn't very many D's here. There were more F's than anything, and the A's and the B's and the C's were pretty leveled out. Then when I go and I look at the test scores over here, though, it gives me much different information about the distribution of the grades, right? I can see that I only have a few 10s. I have less than 10s. I only have a few. Between 10 and 20, I have none. Pretty consistent in the 20s, the 30s, 40 and 50 is kind of low. Remember on that other graph that we looked at, this bar graph right here, all of these numbers make up the F graph. And so that's why the data can be broken up and redistributed and look different in a bar graph than it can in a histogram. But this shows us a much more continuous set of data. Very few people scored in this area, and then as the scores begin to go up, more and more people were scoring between the 70 and 80 range, between the 80 and 90 range. In fact, more people scored between 90 and 100 than any other group of 10s that was shown on this histogram. So that's the first important thing that we want to talk about when we look at the difference between bar graphs and histograms. Another thing I'll mention is in a histogram, it's very important that we take the data and we write it out in terms of frequency. And so oftentimes what you'll see, switch this over. Oftentimes what you'll see before drawing a histogram is a chart that may give you something like range and frequency. Now, when you're making a histogram, the range categories many times are up to you. So it's important to look at the data and decide how do you want to break it up. For this particular example, it was broken up in groups of 10s. Did you have to break it up in groups of 10s? Certainly not. If you were drawing your own histogram, you could have done breaking it up into whatever categories you want. The important thing is that these values for range stay consistent. So if you're going to make the range for the data between 0 and 20, for example, your first set of data, you could make it between 0 and 20 if you like, but then from there on out, every range should have a width of 20. In other words, if you made this one 0 to 20, the next one I would want to make 21 to 40, and then 41 to 60, and so on and so forth. So I'm going by groups of 20, up to 20, and then 40, and then 60, and 80, and so on. So you can break this up in any way you like. I'm actually going to do that. I'm going to break this up. I'm going to say a range from, well, nobody got a, oh yeah, there were 3 people that got a 0 on this exam, so I have to include 0 in here. I'm going to say 0 to 20 for the first range. The next range I'll say 21 to 40. Another important thing about histogram is that the ranges are continuous, and you don't want to put the same value here as you have right here, because then you're double counting. So if you stop at 20, the next one you're going to want to do is 21, so that every value only has one group to fall into. 41 to 60, 61 to 80, 81 to 100. So unfortunately, our range for this one is actually 20, and the rest of these is, or actually the range right here is 21, and each one of these ranges is about 20, but I couldn't do much about that because I had to include 0 as well. But now I can go through, I can look at this data over here. I'm going to use the same exact score data that we looked at before, and I can count it out. So how many 0s to 20s did I have? It looks like I have 3 of them. How many numbers between 21 and 40? 1, 2, 3, 4, 5, 6, 7. How many between 41 and 60? 1, 2, 3. How many between 61 and 80? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then lastly, how many between 81 and 100? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So here I'm generating a histogram for the same data as the one that we have here. All I've done is change the range. So when I generate the histogram, the first thing that I want to do is make sure that I label all of my range values here. So I'll have here, I'm going to start with my 0 value being right here. And remember, I'm moving up by increments of 20. So I'll make 20 right here, 40, 60, 80, and 100 here. So I should have 5 bars for my 5 ranges. Then what I do is I look at frequency and I identify what the largest value of frequency is. It's 15 in here. And that is what allows me to draw the vertical axis. So for frequency, my largest value should be 15. I'll put it up here maybe. And then I can go down here. Let's say, I'm going to go actually in order of 1. 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4. Uh-oh. I got to make my graph a little bigger. You can change the scale of your frequency. Notice I'm going by 1s, which makes this thing a little bit more problematic. I could have gone by 2s or by 5s or whatever is more convenient for me. So maybe I'll go by odds. About 1, 3, 5, 7, 9, 11, 13, and then 15. I got to redraw my 20, 40, 60, 80, 100. And now I just match up. So for that first bar, I want to go to a height of 3. That first bar ends at 20, and it starts at the beginning of the distribution. So my first bar is going to look something like this. Then from 21 to 40, I want to make a height of 7. For 41 to 60, I'm back down to 3. Now I jump up to 11 for 60 to 80. and then lastly, all the way up to 15 for 80 to 100. That's a nicely constructed histogram. We can see that the data is distributed heavy to the right-hand side. In Math 120, we're going to talk lots more about this distribution and what's called skewness, which is when the graph has more weight to one side than another. So that's all about bar graphs and histograms. Let me go to line charts. And line charts is really the exact same thing as a histogram. The only thing that's different is now, instead of using bars, we're using dots. And so what I can do here is I can draw out each one of these values and replace them with a dot and show the line graph as well. And so this chart that we have right here, actually we can look at the similarities between this histogram that we have right here and this line chart that's here. The only difference is that each one of these bars at the beginning of the bar has now been replaced with a dot. So if you wanted to make a bar or a line chart from a histogram, you would start by making the dot on the beginning of each one of these values here. So I'm going to go to the top left corner. Oops, sorry, this is the top. I'm going to go to the top left corner of each one of these bars. That is where our distribution is going to start. And so if I wanted to make a line graph from a histogram, this is where I would place those dots. And then it's just a matter of connecting all of those. I'm going to get rid of my bars. And now I'm going to take these dots here and I'm going to just connect them all one with each other. Again, if you want to do this from scratch without the bars actually, what you would do is you would look at the very left value of your range, the left value of your range, and then look at this as your vertical value. So at 0, remember that down here, this is the score of 0. At 0, I should have a frequency of 3. At 21, I want a frequency of 7. So here around just about 20, I'm going to go up to 7, make my dot. At 41, I want the frequency of 3. At 61, I want the frequency of 11. And then at 81, I'm going to put the frequency of 15. And notice there's no dot at 100. So we're just looking at the left values of the bar. And we just connect these with a straight line. And so there's the line graph. Line charts are really good when we have lots of data points, particularly when you want to do it over time. So this is a really cool example here that has been attached for this line chart. What this shows is the total number of home runs in Major League Baseball by year. And what you can see is that when baseball first started out many, many years ago, there were not very many home runs. And over time, between people getting more athletic, baseballs, the structure of baseballs changing, pitchers pitching harder, outfields changing size and shape, that home runs increase pretty much year to year. And once in a while, you may have a dip in there. But what it shows us is over a long period of time, we can study trends. So without looking at the small peaks and valleys, what we see generally in this line chart is that data is increasing. It's going up, right? It's not consistently going up. Certainly there are years when there's a big drop off in home runs. And of course, we can start looking where is like the late 90s, early 2000s. Oh, like right here. So this is known as like the steroid era in baseball. And you can see that from this point here to this point here, or even this point here, which is like peak steroid era, that the amount of home runs jumped significantly over this time, right? And then steroid era was over, and yes, there's some peaks, but over time it started going down. And then this late numbers here actually is what we think is a change in baseballs. So baseballs started getting manufactured slightly different, and it made a major difference in the projectile of the baseball. And so it turns out home runs did a very, very sharp increase, similar to the steroid era, just in the last few years. So overall, what this graph is showing us is a change over time, right? Connecting all these dots like we did in this one becomes significantly harder with this data. So it turns out that when we have really large data sets like this one right here, we usually allow computer software to do that for us. I would never ever make you try to draw a line graph that's as complicated as this. But I would like you to be able to interpret a line graph just like I did if you were to see one. That leads us to pie chart or circle graph. I refer to them as pie chart. So what is a pie chart good for? And what is a bar chart good for? So a bar chart, the one that we just talked about, and histograms, uh, mainly are showing us frequency. How many times did this occur? How many home runs were there that year? How many A's did I have on my exam? The difference between that and the pie chart or circle chart is that the pie chart gives us a good representation of what's known as relative frequencies or percentages. So it gives us different size slices of the pie, and it's very easy for our minds to interpret different size slices as more. And so this example right here was a candy bar type. We asked 40 people what their favorite candy bar were of these six, and those are the results right there. So what we did is we took all of these values and we wanted to express them as a pie chart. And so before we do that, let's first write them out. We had Three Musketeers. I'm just going to abbreviate these. M&M Peanut, M&M Regular, Snickers, Yum, Twix. Ooh, even better. So we have all these values right here, and then we can write out the frequencies for each one of these. So remember, we're just going to copy this over. We have two people like Three Musketeers, three people like Milky Way, my dad's favorite, M&M Peanut, 15 people like those. My daughter's favorite, M&M Regular, 4 people like those. Lots of people like Snickers. I loves Twix. I loves Twix. So from here, what you should do is you should always add up the total and frequency, no matter what you're looking at, so that you know how to express these as percentages. In this case, I had 40 students that I asked. There were a total of 40 here. And now what I'm going to do is, just next to this column, I'm going to put what's called relative frequency. Relative frequency is a fraction. And so the denominator of that fraction should be the total, and the numerator is the frequency. So for Three Musketeers, the relative frequency would be 2 out of 40. I'm not even going to simplify these fractions. Milky Way, 3 out of 40. Peanut M&M, 15 out of 40. M&M Regular, 4 out of 40. Snickers, 12 out of 40. And then lastly, Twix, 4 out of 40. Now the fractions don't really give me a good I should take that back. A fraction can give you a good representation of a pie chart, but when the denominator is really big, it becomes more challenging. For example, I could take a circle or pie chart and cut it into 40 slices, and two of those slices would be two of those slices would be Three Musketeers, three of those slices would be Milky Way, 15 of those slices would be M&M Peanut, and so on and so forth. But like I said, once you start having a large frequency like 40, cutting a circle up into 40 equal slices is not an easy task. It gets real messy. It's hard to visualize that way. So instead what we're going to do is we're going to take each of these relative frequencies and we're going to get our trusty calculator and we're going to express these as a percentage. And as a percentage, then it becomes a little bit easier to kind of visualize where it should go on the circle. So 2 out of 40, 2 out of 40 as a decimal is the same thing as 0.05 or 5%. 3 out of 40 is 7.5%. 15 out of 40, 37.5%. 4 out of 40, 10%. 12 out of 40, 30%. And then another 4 out of 40, which is 10%. Now we're ready to start drawing this thing out. And for now, just give it your best guess. It doesn't have to be perfect, but there should be some certain things that you're looking for in terms of pie slices. When you do the homework on MyMathLab, be very careful to look at the pictures for pie charts. Kind of annoying. You have to make sure that your pie slices look good, and they give you all these different options where slices are changed. That's not a very good pie. I feel like I want to do it again. Do I have any? Ah, here we go. Got a trusty water bottle here. No, that water bottle's not going to work. Oh, here we go. Got a trusty Gatorade bottle here. I'm going to use to trace my pie chart because my circle is terrible. And that wasn't much better, but I guess it's a little bit better. So there's a location for my pie chart. And then what I would do in generating the pie chart is to look for percentages that line up nicely. And what I mean by that is it's really hard to make a slice that's 37.5%. But if you look at a group of percentages that maybe add up to something that's a little easier to make, that may be the way to go. And so I'm actually looking at these bottom three right here, 10%, 30%, and 10%. And I know that together they add up to 50%. Similarly, the top three, 5%, 7.5%, and 37.5%, also add up to 50%. So what I could do in the very beginning is take this graph and cut it in half. Didn't have to be a vertical line, it could have been a cross. But what that does now is it tells me, okay, I can take these three values right here, and they should be broken up on this right side. And then I'm going to take these other three values up here, and I'm going to break them up on the left. Now, if I were to go straight across like this and cut this in half, what it would give me is a 25% and another 25%. So half. Half of a half is a quarter. A quarter is 25%. But right here, this isn't exactly what I want because I don't have a 25%. I have a 30%. So I'm going to make this line a little bit bigger than straight across. Maybe like this. And in here, I'm going to put my Snickers. Now I have this extra slice down here, which should be a total of 20%. I'm going to take this 20% and I'm going to cut it in half. And what that does is it gives me two slices that are each 10%. One of them can be M&Ms. One of them can be Twix. Then I go back to my percentages up here, and I have a 5%, a 7.5%, and a 37.5% that I need to make. Now remember that this Snickers slice is 30% right here. So when I make this M&M peanut slice, 37.5% on the other side, it should be a bigger slice than this Snickers slice. I'm going to go down maybe like that. I'll say that that is my peanut M&M. My last two were 5 and 7.5%. They're different. I don't want to make this slice equal like I did in the last one. One of the slices should be slightly bigger than the other. Again, just give it your best eyeball. I will be very nice to you when it comes to judging your graphs. And I'm going to say this little tiny slice right here is 5%. That's my 3M or my Three Musketeers. And then this tiny slice over here is going to be my Milky Way. And there's our pie chart. The last display of data that we're going to discuss is all about scatter plots. And scatter plots is very similar to the stuff that we were talking about in line graphs. What it does is it takes a lot of information and it plots it all over the place. The difference between a scatter plot and a line graph is a line graph usually shows a change over time. And there's only one unique value for each one of those times. So we go back up here real quick to look at this home runs. Each one of these values is only represented one time. And then when I connect those dots, it gives me a trend over time. In the scatter plot, what we're doing is we're taking lots and lots of information. This is a giant set of data here that shows all 50 states, and it shows how much on average you make in your house, the median household income. We know what median is now. And so we arrange all these from most expensive to least expensive, and we find the middle value. And that's what the median is. So for Alabama, you could take every person's household income, arrange them from largest to smallest, and it turns out that the median value is about $45,000, right? And it varies from state to state. It looks like Alaska has a very high median. It's really interesting, like $73,000 in Alaska, as opposed to just $44,000 in Alabama. So we take all that information, and it's important that we want to see if there's some kind of trend or relationship between two things. And so in this problem, what we did is we wanted to look at your median income. So how much on average does somebody make in your state? And compare that to the number of new passports that are issued. So the idea is that, or the theory in this problem is that the more money you make on average, the more likely you are to travel outside of the country, the more likely you are to get a passport. So people that are in more affluent states or states that make more money are more likely to travel out of the country. So the relationship here is plotted, and you can see that for all 50 states, there's no exact rhyme or reason. There's not a perfect trend in here. But we do see a pattern emerging. We see this clustering of data that kind of follows this like similar line right here. It doesn't follow the line perfectly. You can see there are values that are way off of that line up here. There are values that are way below that line right here. And so for various reasons, some of these don't necessarily have to follow the trend. But when you get a lot of data, like all 50 states, it gives us an overall picture of if there is a relationship there. Is there some kind of cause and effect? So that gets us to the idea of what's called correlation. So correlation describes the relationship between two things in terms of two things: strength, so how well do you fit on a line, and direction. Are you trending upward or are you trending downward? So we always read a graph from left to right. And as we read a graph from left to right, if it's increasing, if this trend line is increasing, then we say that that correlation is positive. If, as we read from left to right, the direction is heading downward, then we say that you have a negative correlation. So that's the direction part. In terms of the strength part is defined as how well do you fit on a line. Now, correlation can range between +1 and -1. A correlation of 1 is very, very strong. You can see that we have this data that fits very well along a line. Whereas data that doesn't kind of fit so well on a line, that's kind of spread out, has a much smaller correlation coefficient, or much smaller number related to correlation. As that number gets closer and closer to 0, then no pattern is emerging at all. There's no relationship between these dots here. I couldn't make a line that connects them very well. And then you see that they start to cluster closer together again. But if we read them from left to right, they're on their way down. And this is why we have this negative value here for correlation. And in here we get even stronger correlation. And then this right here where they all fit on a perfect line, perfect correlation. So going back to our scatter plot data that we had right here, we can see that lots of these points fit either right on the line or very, very close to the line. And what that shows us is that there is a very strong correlation here. It's really hard to see, but we have a value down here. It's kind of blocked by this point, I apologize. But it tells us R is equal to 0.71. R is a symbol that we use for correlation, and a correlation coefficient of 0.71 is pretty strong. It's not 1, it's not perfect, but it's definitely a lot stronger than perhaps, say, this or no correlation at all. So what this is telling us is that there is certainly a relationship, and the relationship is that the more passports that are being issued leads to or is a result of more money in your state. So you make more money, you're more likely to travel. So that's all about scatter plots. In Math 120, we do a great discussion on scatter plots and correlation. I won't be asking you very many things about correlation this semester. However, it is important to just kind of know the idea and what it is, what it means, because when we get into 120, we're going to do lots of tough work with it. So that's it today.